Okay, today I'll be talking about the optical aspects of semiconductor lasers. As you know, semiconductor laser is a device in which coherent photons are generated by interaction with electrons and holes. So it is not just a electronic device. In the laser cavity, we are having strong interaction between photons and electrons and holes. So the aspect of waveguiding is very important. Optical confinement is very important, and the modal distribution in the semiconductor laser is very important. So today I'll be talking about what is known as the confinement factor, gamma. As you will remember, this came in to the expression for the threshold current, confinement factor gamma. And what I want to do is derive the value of gamma and show how it depends upon the width of the active layer. I have drawn a slab waveguide structure, which I described last time. And this is consisting of an inner active layer refractive index N2 of thickness D. Take the axis, x-axis in this direction. The thickness is D. Sandwiched between two barrier layers, or in the fiber optic jargon, these are cladding. Okay, this is core and cladding. But in semiconductors, we call this the active and the barrier. And we want to see what happens to light that is being generated in this active region. For example, the quantum wells or the PN junctions are all in this active region. And this has a slightly different refractive index. And we'll see what is the condition for waveguiding. It's the same as in the case of the optical fiber. And if D is comparable with the wavelength of light, we find that the total light intensity or the light energy is no longer confined within this active layer, but it spreads out, and the typical profile could be a Gaussian profile of this type. Okay. And gamma is defined as the light intensity within the active layer to the total light intensity. Graphically, one can say that suppose I shade in this region, which is it's the area of the shaded region to the total integrated area over this under this curve. So in case D is very large compared with wavelength, gamma will be unity, and so gamma will typically vary from 0 to 1. Okay, and from the physics, one can see that it will depend upon this width D, obviously, and it will depend upon this wavelength difference N1, N2, N3, the wavelength profile. Now, for the sake of waveguiding, from the point of view of geometrical optics, we know that light will be reflected if the angle of incidence, if we have this relation that N2 is greater than N1 and N3, they may be equal or different, then we have total internal reflection, and I gave you the the relation theta theta c is equal to sine inverse n1 by n2, right? And this critical angle is very small. It's only about 16 degrees for gallium arsenide. So you can think of it from the wave, from the geometrical optic point of view. You can think of it, the light will, okay, and be reflected here and go back and forth. We have a reflecting mirror here, so it'll traverse this cavity repeatedly and interact with the carriers which are injected here and give rise to stimulated emission. Okay, in order to calculate gamma for a particular structure, we have to use the wave equation derived from Maxwell's equations. And so we'll do that for a particular case for TE modes. Now, we know from Maxwell's equations that curl of E is minus delta B delta T, and curl of H is equal to the conduction current plus delta D delta T, the displacement current. From this, we can define in a waveguiding structure transverse electric waves, and with Z being the direction of propagation, transverse electric waves, the definition of this is that Ez must be equal to 0. Okay. And if Ez is equal to 0, then from these equations we have Hy and Ex also equal to 0. So there is no longitudinal component of the electric field. That's why it's called transverse electric. And we have transverse magnetic waves, in which by definition Hz is equal to 0, and for this Ey equal to Hx is equal to 0. So in 3 dimensions there are total 6 components, of which 3 become 0 if we take transverse electric or transverse magnetic. So this helps the solution of the wave equation. And the wave equation is then, from Maxwell's equations by substitution, you derive the wave equations. Del 2E is equal to mu 0 epsilon delta 2E. Relation between the spatial and the temporal variation. Notice these are non-magnetic materials, so mu is equal to mu 0, but the dielectric constant epsilon is epsilon r into epsilon 0. Similarly, we have the relation for time-varying magnetic field, mu 0 epsilon delta 2h delta squared. Okay. So we want to solve these equations with the condition that some of the components are 0. Okay. If we take this into account, and we are talking about this being the z direction and this being the y direction perpendicular to the plane of the paper, then the wave equation simplifies to delta 2 for TE waves. Okay, let's for TE waves. Delta 2 Ey delta x squared plus delta 2 Ey delta z squared is equal to mu 0 epsilon delta 2 Ey delta t squared. Okay, this is the general equation. It has to be solved both within the active region as well as in the barrier region. In the active region, that is x lying between minus d by 2 and plus d by 2. We assume a solution EY, which is a function of x, z, and t. We are assuming that the variation delta delta y in the y direction, this direction, is equal to 0. This is given by some amplitude term AE cos kx, the propagation constant, e to the power into e to the power j omega t minus. Okay. This is the propagation constant, beta, in the z direction. Okay, k is a parameter describing the variation in the x direction. X direction is this direction. Okay, this is x direction. This is so. For example, you can have different modes. Variation along x will give us different modes, and this is the z direction. And if we substitute this back in this expression and equate the left hand and right hand side, we'll get a relation. Obviously, k squared is equal to n2 squared k0 squared minus beta squared. Beta is a separation constant, and what is k0? K0 is obviously related to the properties omega over n2 into this mu 0 e, mu 0 epsilon. Okay, so we assume that this is the solution for the electric field in the y direction. EY is connected to 8z. So similarly, we have 8z xzt, and it's just given by j over omega mu 0 into delta EY delta x. Okay? So if we know EY, we know 8z. And if we just substitute, we find that this is equal to j by omega mu 0 it becomes minus jk. Okay, this is delta EY delta EX, so we are differentiating here. Okay, the cos becomes minus sine, so minus j k AE sine kx into exponential e to the power j omega t minus beta z. Okay, now we can find okay, so this is within the active layer. Outside active layer, where the magnitude of x is greater than d by 2, then there we have a damped wave, because there is no stimulated emission going on. So you can get the solutions for EY and 8z as before. And we find the separation constant beta from equating the boundary conditions between within and without the layer. So outside the active layer, we have EY xzt but we have a damped wave, AE cos k d by 2 exponential minus gamma, okay, so there's no j here, minus gamma x minus d by 2 into x j, the old omega t minus beta z term. Okay. This is a diminishing term because, as we saw here, the intensity here is decreasing as you go into the barrier layer. Okay. Similarly, one could write for 8z xzt is minus x by the magnitude of x. Okay. J omega omega mu 0, it's the old relation, AE cos k d by 2 into x minus gamma, again x minus d by 2, where x here is now larger than d by 2, so this is something positive, into exponential j omega t minus beta z, where if you substitute back in that original equation, you have a relation between gamma squared is equal to beta squared minus n1 squared. Okay. Now the propagation is in the outer region, so let's take n1 is equal to n2. We can say that n1 is equal to n3. Okay. So symmetrical waveguide, k0 squared. Okay. So this is one crucial equation relating n1 k0 gamma with beta, and the other within the active region we have this relation, okay, relating n2 k0 and beta. Okay. Now we want to find beta, and we want to find out what are the conditions under which this wave propagation is satisfied. So we know that since both k and gamma must be positive and real, in this is positive and real, so this must be larger than that. Okay, so we have beta squared must be larger than n1 squared k0 squared. That is one relation. And from this relation, if k is to be real and positive, this must be larger than that. Okay. So we have n2 squared k0 squared greater than beta squared. Okay. And so if you look at this, this should be greater than n1 squared k0 squared. Okay, so what is the condition if you just cancel these? Then obviously the condition is that n2, I've left out the bars here. Okay. N2 must be greater than n1. Okay. So we are back to the original equation that in the waveguide structure, to get confinement, to get optical confinement, n2, the middle active region must have a refractive index greater than n1. In practice, this is realized. Why? Because the central layer is gallium arsenide and the outer layers are gallium aluminum arsenide. Okay, so it is practically realizable. Okay. Now, to find beta, you have to work this out for yourself and satisfy yourself that the arithmetic is correct. We use the boundary condition at x equal to d by 2 that the tangential component Hz must be continuous. Okay, Hz is the magnetic field in this direction. Okay, the tangential component here going in the, okay, this is say plus d by 2, must be continuous across this boundary. Okay, Hz. For even T modes, even meaning symmetrical with respect to x, the relation then is, if you look at the values of Hz, take the value of Hz, greater than x greater than d by 2 and x less than d by 2, and you equate it, then you find that the condition is that kd by 2 tan kd by 2, because there's one in one relation there's sine, the other relation there's cos, so you divide, you get tan kd by 2 is equal to gamma d by 2. Okay. And so this cancels d2. Okay, so you have then tan kd by 2 is equal to gamma by k, and from those relations A and B, we know what gamma and k are. Okay, so gamma is this, gamma squared is this. Okay, and similarly k. So gamma is just b squared minus n1 squared k0 squared, and k is given by n2 squared k0 squared minus beta squared, okay, to the power half. Okay, so tan is the solution depends upon the argument of the tan function. So you have multiple values. For if you have a tan value and you add for addition of another 2 pi m, you get the same values, and m is equal to 0 gives you a fundamental mode. Okay, m is equal to 1 gives you a higher mode, etc. So these are modes which describe the variation of the electric field, okay, in this direction. Okay, you may have, this is one mode. You may have multiple maximum, okay, as you go in this x direction. So the higher modes will have fundamental mode has one maximum, higher mode, next higher mode will have two maxima, etc., etc. So you will get different distributions of electric field in this direction. Notice that higher modes are not desirable. Why? Because if this is radiating. After all, this is a p-n junction. The light output will come out from here, from this region, and the light output will be something like this, right? Radiation pattern. Now, if you have a higher mode, you will not get one maxima. Okay, you will get the maximum will be split. You will get, so that is not very desirable. Okay, so I'll show what the pattern is for. You will not get one spot, then you will get two spots or three spots. Okay, so that itself is not very desirable. Okay, now to come back to calculation of the value of gamma. What is gamma? It's proportional to light intensity. What is light intensity? Light intensity is proportional to E into H, okay, power, Poynting's vector, and E into H is proportional to EY 8Z. 8Z is also proportional to EY, so it's proportional to EY, magnitude of EY squared. Okay. So gamma is proportional to EY squared. We have the value of EY we've calculated, and the numerator, it's this EY squared, which is cos. We can neglect the variation with time, so it's cos squared kx dx. Okay, x going from 0 to d by 2. The rest of the terms, AE and all, cancel numerator. And in the denominator, we have this term within the active region, cos squared kx dx, plus the term which is outside the active region, so going from d by 2 to say infinity. And here we have cos squared kd by 2. And there is the exponentially decaying term, exponential, and it's cos squared, so therefore you get, instead of gamma, you get minus twice gamma, okay, x minus d by 2 dx. Okay. This is the intensity within the active region, this is within the active, and this is within the cladding. So if you work this out and you simplify, you get a gamma is equal to, you divide by the numerator, so you get 1 over 1 plus, okay, cos squared kd by 2. Okay, over gamma d by 2 plus 1 by k sine kd by 2. Okay, sine kd by 2. Sorry. Into cos kd by 2. So you would like this, if you want gamma to be large, you would like this term to be small. The values of k, we know that, for example, k squared is equal to n2 squared, k0 squared minus beta squared, and k0 is like a wave number, okay, so where k0 is equal to omega n2 root over mu 0 epsilon. So numerically, this is, all these are known. Okay, all these are known, so you can plug in here. Beta you can calculate from the boundary conditions. So all this is known, and you can actually, D is something that you can vary. Okay, you can choose your active region width according to electrical and optical requirements. And so one can actually plot gamma, maximum value 1, minimum value 0, okay, as a function of D. Say varying from 2 microns to 2. And as you would imagine from intuition, as D decreases, confinement factor decreases quite rapidly, and you get a variation something like this. Okay. So remember, the wavelength of light we're talking about is about a micron. So if the active layer thickness is 2 microns, gamma is almost unity. Okay, but then when it you can see intuitively, when D becomes less than lambda by n2 bar, Okay, what is the wavelength of the light in this medium? Lambda by n2 bar. Okay, and n2 is of the order of 3. Okay, so if this is lambda is say 1.5 micron. Okay, and if this is 3. Okay, so that means when d is less than about 0.5 micron, purely from the optical condition of confinement, the wavelength, if the confining region wavelength dimension becomes much less than the wavelength, at about, okay, this is about 1 micron. Okay, so this is about 0.5 micron somewhere here. Okay, so below 0.5 micron, gamma decreases very, very rapidly. Okay, so this follows from this numerical result. Now I have drawn one particular curve. For certain values of n1 and n2. Now, why does confinement occur? The reason is that n2 is greater than n1 or n3, and that is because if we look at the material aspect, we're talking about N2, say, bar of the active region, gallium arsenide, aluminum arsenide. Just as aluminum is the same size as gallium, because it is more electronegative, aluminum arsenide has a higher band gap, but lower refractive index. And this can be plotted quite accurately by, for gallium arsenide, the refractive index is 3.59, and it's almost a straight line going down to something like 2.97. Okay. So, fortuitously, when we are forming a heterojunction, what are we doing? We have this is gas, this is gas, okay, where aluminum has a particular composition x, 1 minus x. So this is x. So we can read off, for a particular value of x, we can read off what is the refractive index. And this is actually given by a fairly straightforward expression, empirical expression, nx. This refractive index is a function of x. It is obviously 3.59. That is that. There's a minus a linear term 0.71x, and there's a slight bowing plus 0.091 x squared. Okay, so this is a minor term, but it's almost linear with respect to x. Okay, so immediately it tells you that when you choose a particular composition x, you are controlling this, the electrical. Okay, because why? Because you're controlling this. You're controlling this band gap. Okay. As x is increasing, this band gap increases. Okay, and as band gap increases, okay, refractive index also decreases. But we do not go to aluminum arsenide. Why? Because aluminum arsenide is an indirect gap material. Okay, and more the aluminum, the more unstable, the more chemically sensitive the material is. There's a lot of interest in trying to get aluminium-free devices now because of oxidation problems, growth problems for aluminium. So typically, X is kept to 0.2 or 0.3, etc. So, okay. So now you see that if this is D, okay, N2 minus N1, okay, is obviously proportional to x, okay, is a function of x. So confinement factor will also be a function of x, and if you go back to this diagram, I have drawn this for a particular value of x. This is not a very, this is for x is equal to 0.6. A lot of aluminium. Suppose you reduce aluminium, what will happen? Obviously, the refractive index difference will be less, the confinement factor will decrease, and it will go something like this perhaps. And this is for x is equal to 0.1. And notice for x is equal to 0.1, this is I've taken two extremes. In actual practice, x will be something in between 0.2 or 0.3. But look at x equal to 0.1. For 0.2 micron, remember for the low threshold current, 0.2 micron for a double heterostructure was pretty good. But for 0.2 micron here, this gamma is only 0.2. Okay. So this is not a good condition. Okay. On the other hand, for x equal to 0.6, gamma is okay. Gamma is quite large. Gamma will be somewhere here. But from the growth point of view, x is equal to 0.6 is too large. It's the indirect gap region. Okay, so x is a very, very important parameter in controlling confinement factor, and of course d. Okay, d comes into this relation, and you can for all types of structures, as d decreases, obviously confinement factor will come down. And if you remember the relation that what is JTH, J0 eta by d plus J0 no. Okay. And gamma is in this denominator, right? Okay, so we want high gamma to reduce JTH. I have a picture of the, I'm not sure whether it will be visible. This one is an actual picture of confinement factor versus D for double heterostructure. And there are two lines, if you can see. One is transverse electric and the other is transverse magnetic. Okay, I've done the derivation for transverse electric, but this shows that there is not too much difference in gamma. So the structure itself does not choose between transverse electric and transverse magnetic. The confinement factors are almost the same. However, if you want one type of mode to prevail, then mode selection is done by having the reflection coating to be selective. It will choose the transverse electric rather than the transverse magnetic. Okay. Here, okay, since there are relations here, this is for a gas laser. Okay, this is spread out 0 to 0.4 microns, confinement factor gamma. Again, here is indium gallium arsenide phosphide, indium phosphide laser. Okay, so this is slightly less. You can see typically for 0.2, confinement factor is about 0.5, 0.4 or something. You do not want it to go down. Okay, now this one is instructive if you can see it, the last one, confinement factor. Quantum well. Take it to the extreme. Active layer thickness is 20 nanometers, 240 nanometers. Okay, so quantum well can give you a lot of advantages from the point of view of the electrical properties. Okay, you get strong recombination. However, look at confinement factor here. The y-axis. This is 0.03. Okay, 0.01, 0.00, 0.001. So you put 0.001 in the denominator, and JTH will just shoot up. Right. So this is the problem that one has to circumvent if you want to. This is an indium gallium arsenide phosphide, indium phosphide single quantum well. These are sort of things that we are making, and these are three graphs are for three different wavelengths. Three different wavelengths will give you slightly different composition. So confinement factor is a very important plays a very important role. Not only in determining, okay, confinement factor gamma, not only defines JTH, okay, but also the mode, the different, you want a single mode, and also divergence of the light coming out. I'll just show some diagrams to illustrate this. Again, if you plot numerically, you can show that as a function of okay, now we are going in the x-axis. Okay, so this is minus 1 micron. Okay, this is plus 1 micron. And this is the intensity, relative intensity. Okay, I by I0. Okay, and for a laser which operates at 0.9 microns, okay, gives the composition. What happens is X varies. X is the aluminum content. Okay. We expect that as X increases, refractive index difference increases, so confinement will be better. And sure enough, if you look at the distribution, this is for X is equal to 0.1. Suppose you take X is equal to 0.2. That's X equal, sorry, it will be symmetrical, that's 0.2. And X equal to 0.3 will be even sharper. Okay, this is 0.2 and this is 0.3. Okay. So the beam will be much narrower in the X direction as you go towards higher values of X. Now, another variation one can show, suppose you keep X constant and vary D, then what happens? You can draw a similar modal pattern. This is the center, going again in the X direction, minus 1 and plus 1 microns. For D, we find that for double heterostructure lasers, D equal to 0.2 is sort of optimum. So for D equal to 0.2, one gets a pattern. Suppose you make D even less, then what happens? You're trying to squeeze the light, but light diffracts out. As a result, now, as you're reducing D, the light intensity spreads. Okay, and this is for, say, D is equal to 0.075 microns. Okay. So remember, this is what is responsible for the minimum in JTH. Remember the curve of JTH versus D. It's initially linearly proportional to D, and it comes down, and then there's a minimum value at about, say, 0.2 microns for, and thereafter JTH shoots up. Why is that? Because gamma goes down very drastically. Okay, one final graph. What about the modal pattern for different values of M? How do you get different modes? Again, the intensity, relative intensity, I by I0. And this is for the, this is again in the X direction. For the M equal to 0 mode, you will get one. This is the desirable mode, that one that you want. You want a single peak of a Gaussian nature. But if m is equal to 1, then what will you get? You will get a minimum here, in fact. Okay, you will get a distribution which is okay. This is m is equal to 1. So right on axis there will be actually a minimum, and I'll show next time that in this case you will get two bright spots. In the far field. M equal to 2, what will you get? M equal to 2 you will get okay 3. So you m equal to, this is m equal to 1, m equal to 2, you'll get, and m is equal to 1. Obviously this is not good because you're not getting any light on axis and the light intensity. And here m equal to 0, you will get one strong pattern. Okay. So this is looking at the, here's a laser, the active region, okay, and this is the z direction. When the light comes out, okay, we're looking at the pattern of light that is coming out of the laser, the distribution of light. And in the case of, this is for m is equal to 0, the fundamental mode. So to sum up, confinement factor is a very important parameter in semiconductor lasers. It determines not only the threshold current, it also determines the modal current, modal distribution of intensity and the stability of the laser in the far field, and that determines its applications in fiber optics and in long-range LIDAR type of applications.